name is Camille, and I'm doing a PhD here at the Cavendish labs. My subject is a part of physics that really was not created, but really worked on starting in the early 20th century, when people realized that scientists realized that the laws that they had been using so far and that using to explain phenomena in nature, such that Newton's laws, would not explain some of the phenomena at a very, very small scale and scale of the atom, for example. And so they had to invent a new theory to explain those observations, and that is called quantum mechanics. Quantum mechanics is called quantum because everything it describes is quantized. So for example, atoms don't have a continuous energy. They can't take any value of the energy. They have energy levels, just like, for example, gears on a bicycle. And so by using different ways, so excitations of different nature, in particular light, we can switch those gears in the atom, and we can play with the energy levels, just like using a derailleur on a bike. And that's what we're trying to do on some atomic systems. So in terms of atomic systems, there are many ways we can capture them and study them. So for now about 20 years, people have been using very tightly focused laser beams to trap atoms and then manipulate them. But of course, this is difficult to maintain. So in my case, we use crystal lattices to trap atoms in them. So we trap impurities in diamond lattices, in my case. And so those atoms then are isolated from each other because the density of impurities is low, so they don't see each other. And so we can really address them individually and play around with them. So in terms of where it could lead us to in the future and how we could use that technology, actually those single atoms are very sensitive to many, many things. So they can be used, for example, for sensing. They can sense very, very tiny magnetic fields or temperature changes. So some people are trying to make also nano diamonds with those impurities and put them into cells and monitor cells metabolism and things like that for cancer research. They could also be used to store information or process information, just like bits in a computer, but using energy levels in the atom rather than series of zeros and ones. So in some sense, some sort of quantum computing using those atoms. There are some peculiar properties to quantum mechanics, and a system can be in different states at the same time. This was illustrated in the 1930s by a physicist called Erwin Schrödinger, who was one of the first ones to really work on this quantum superposition principles and the laws of physics that describe quantum systems. And he said, well, it would be like having a cat which is both alive and dead at the same time. So what we have nowadays in computers is we have chips with lots of transistors on them. And those transistors are a bit like switches, and they can be, you can tell them, okay, let electrons through or block them, and then you can switch them between zeros and ones, so you can create series of zeros and ones and use that to code information. But you have to have as many transistors as operations you want to run at the same time. But if you have a quantum system, because of this superposition principle, then you can have all those bits superimposed in one system. So you just need one system to have a multi-bit computing power. So nowadays, people have been working mainly on the quantum cryptography side, and so ways of sending information that is protected by the laws of physics. For example, you encode something on a photon, and then you send the photon into a fiber, and an optical fiber, and then you receive it at the other end. First of all, you need to know how to decode it, to read it. But also, if you measure a quantum system, you modify it. So if a spy interrupts it at some point, then it just destroys it, basically, and you know immediately that someone read it at some point before you. So people have been mainly working on that because of all the commercial interests we know. And it's starting to be implemented. There are some networks now between different cities in the UK. In terms of quantum computing, it's not so much developed at the moment. There are some difficulties because those are single photon emitters. It's very hard to collect those photons to lead them to detector. There's a lot of noise. There's things that can go wrong, and for the moment there are many things that need to be optimized really. So when I'm done, trying to send photons on single atoms, I just go and I take a gouge and I carve wood until it finally, hopefully in a couple of years or so, make a cello. But for the moment, it's still it's getting there.